Fun. Okay, we're good to go. I'm gonna stretch. I'm relaxed. I feel like it's darker in here. I feel like this lower light is more important, so I feel more lit from below. I finally can turn my hat back around. I didn't want to be in the dark for so long. I got some new pens. I'm stretched. I washed most of the Expo marker off my hands. Feel great. Still have this corner. I think it's like a birthmark now. So we're going to look at recurrence here. I think, are we on frame? Yeah, we're big here. I'm big. So what is a recurrence? Recurrence, and I'm just going to label it maybe some recurrence. This is A, we call it like here, maybe A sub 1, A sub 2, A sub 3. Goes on pretty much infinitely. I'll just find a simple recurrence where this is just like a first order. Is given by an initial value. Value, maybe A sub 1. And a relationship between successive terms. So this is A1, A2, A3, all the way up to infinity. We might not get there in time. And so we have a relationship between successive terms. So we'll go over what that sort of looks like right here. I'm going to define one recurrence right here. Here we have A sub 1 equals 1. And then I'm going to say, I'm going to define the relationship between, so this is like an initial value. And maybe then I have A sub, in general, n equals 2 times A sub n minus 1. So it's relating here. I have an initial term, and then I have a relationship between successive terms. So what is this sequence? So here we have, this sequence looks like 1. The next term is twice as big as the first one. Maybe we'll say this is also for n bigger than 1, or n greater than or equal to 2. We need this recurrence to be true. So it looks like 1 for the first thing, and then I double that, 2. And then the third term is twice as big as the second. So then you get 4. The fourth term is twice as big as this one, 8. Continuing, 16, 32, 64, 128, 256, 512. We've seen a lot of these numbers. These are powers of 2. So if you start with 1, you double it each time, you get these powers of 2 popping out. So this is one way we can define all the powers of 2 using this recurrence. So this is one way to phrase something. This is also the most straightforward form of recurrence, and so this is maybe just a baby recurrence. Although these can be quite involved as well. I don't want to, maybe some babies are bold. We can also have a recurrence. A recurrence can relate A sub n to any number of terms A sub 1, A sub 2, all the way up to A sub n minus 1. In which case we might need to provide more initial values. So the idea is, what's going on with recurrences to some extent? There's sort of this idea of, they're telling you this process of like, when I'm in the middle of this, like this is how things continue, that's this relationship, or it's a relation. And they start off with some sort of initial value. So that sort of gets the ball rolling. And then you say, okay, once I have my initial value, I just start doubling it over here. And so later on, maybe I need a couple values to get the ball rolling, but I can tell you something based off those previous ones. So we'll go through an example using this form of a recurrence first. Then we'll go into a couple that use recurrence that relates a term to actually the 2 previous. This is a super underground recurrence that you might not have heard of, but it will be you hear of now. And that's what you're here for, I'm sure. And then we'll hear some more. Cool. All right, we'll go on to the next. I'll go small and do some erasing. I think the happy medium, now that I think about it, the happy medium would have been every time I don't flip the camera, I have to take that many increasing sips of water. Hydration is important, as was stated before. Okay, so suppose we have n lines drawn on the plane in general position. So this means that there's a couple ways for lines to do funny things. They can be parallel, or a bunch of them can intersect in the same point. So here we're saying we have a bunch of lines drawn on the plane in general position, such that no two are parallel, no three lines meet a common point. So I want to construct a recurrence for the number of regions r sub n created by these n lines. So let's think about this first. So first, maybe I have the plane, and I want to think about R1. R1. So R1 is going to tell me how many regions the plane is split into by a line. So I have the plane, you can think about it extending infinitely, and I draw a line in some fashion. Okay, how many regions have I split the plane into? Two, yeah, this is, yeah. Oftentimes it's nice when our recurrence starts off not so bad. Okay, next, R2 means what's going on? I have my previous line, so I put that one in here, and I'm going to add another line to this picture. Take a sip. Okay, so I'm going to add another line to this picture. I can't draw a line that's parallel, and I don't want the line to cross through two previously drawn ones. That's not an issue yet, though. So I'm just going to draw another line that's not parallel, like this. So they intersect right here. And I'm going to notice something first. How many regions has the plane been divided into now? Anyone know? 4, yeah. Equals 4. All right, I'm going to now draw or highlight some idea. Okay, so I noticed that this line, my newest line that I've drawn, is split up into subsegments, smaller segments, based off of intersection with other lines. So this line right here, my newest line, is split into these two subsegments. And each subsegment is traveling through what used to be one region, and it splits it into two. So this subsegment turns one region into two regions. This subsegment turns one region into two regions. And we're going to keep that idea going. Let's see what happens when we have R equal R3. R3. So I first have this line here. I drew my second line here. They cross right there. So I'm going to put a third line down. So it can't be parallel to any line I've drawn before, and it also can't pass through this intersection. So no matter how you do this, so sometimes like maybe it looks like this. This is just one version right here, but you can think of these in a couple different ways. So I'm going to notice, okay, this is my third line. It intersects both of my previous lines, and they're all in different points. So all these intersections are in different points. It has to intersect because it's not parallel. So it intersects all of the previous lines. And you'll notice that here we had one line in one segment. In this one, our newest line got split into two segments. And now my third line right here can be split up into 3 different segments. So my third line splits all the previous ones and is split into 3 segments. Let's look at each of these segments. Each of these segments passes through what was once a region. All regions are bounded by lines, so as it goes through, it's right here. This segment, or this region right here in the plane, was split into 2 across segment 1. This region right here was split into 2 across segment 2. This region down here was split into 2 across region 3. And this gets at this idea for like what's going on in general. If we want to think about R, so then this ends up being, right, you can think 1, 2, 3, 4, 5, 6, 7 equals 7. So we started with 2, and then we were 2 bigger, and then we were 3 bigger. Maybe there's a pattern. So let's look at R and So like, suppose you have n minus 1 lines already placed in the plane. Already placed in the plane. They divide it into, dividing it into capital R sub n minus 1 subregions, or regions. Okay? And I don't know what that number is right now. This is one of the powerful ideas within a recurrence relation. I don't necessarily know what this is, but I am going to be able to figure out how Rn relates to it. So I don't know what this is, but I will be able to find a relationship between those two things. So they divide it into R sub n minus 1 regions. Okay. Place an nth line. Okay? So we're in general position. So not parallel to any of the ones before, not intersecting three ways with any of these. Similar to this idea here, right? When we cross two lines, our newest line got split into three. Our new line, this nth line, will intersect all n minus 1 and will be divided into n subsections. It can be partitioned in this fashion into n subsections. And again, each subsection splits a previously defined region into two. Each splitting a region in two. Okay? And so let's think about this. So they each split a region in half or into two pieces, and they all split different regions into two, right? Regions are split off by lines, and these segments are on either sides of lines. So two regions can't be on different sides. The same region can't be on two different sides of one line. So the idea is this region over here can't be the same as this region over here because it's across this line right here. So each one partitions, so each one splits a region in two, and they all split a unique region in two. So we've split n regions into more regions. So after doing this, we have the number of regions we started with, which is R sub n minus 1. And we've taken n of those and we've doubled them, so we gain a total of n regions plus n regions. Is that clear? While we split them in two, we don't add 2n because we started with n of them. So we take n that we had and we turn them into 2n. All right. Okay, so what does this mean? That Rn should be equal to Rn minus 1 plus n. So Rn is equal to, you take the number of regions you had before, and you add n. So this defines the recurrence in conjunction with this idea right here, also with the idea that R1 equals 2. Okay, awesome. Questions on this thing right here? People feel okay? Everyone feels great? I also feel great. Thank you for asking.
Are you going to tell us what the closed form of that is?
I was going to avoid telling people the closed form of anything because we didn't have to. Because I didn't want to define a closed form. So
that's fine. Maybe I can prove it then.
Yeah, that seems like something that you, yeah. I believe in you. I think you can.
Introduction to do it right.
Certainly, yeah, it is, yeah. To do it. But you'll notice that this is 1 plus 1. Maybe I'll suggest something. Yeah. This equals 1 plus 1. This equals 1 plus 1 plus 2. And this number here equals 1 plus 1 plus 2 plus 3. And Corey can maybe tell us what's going on underneath these curly braces or above these curly braces in like a couple hours from now. That could be fun. It's nice to have those sorts of breadcrumbs to look forward to. All right, so this was an example of our first form of recurrence, where each term was defined just off the previous one, right? We figured out Rn just based off of Rn minus 1, and then some other function, just in terms of n, though. We were able to figure that out. So next we have a situation where a breeding pair of rabbits is placed on an island. And they're young, I guess. They're not quite old enough to breed. They're just newborn, but people know they can go, and they're rabbits. So a pair of rabbits does not breed until they are 2 months old. After they are 2 months old, each pair of rabbits produces another pair each month, and they keep doing that forever. This is like, I guess, some sort of, nice island where rabbits don't die, and they go and they make rabbits all day. Okay, so after they don't reproduce until after they are 2 months old. So here we're going to look at a recurrence where we have a sub n is going to be the number of pairs of rabbits on the island after n months. And so we want to figure out our recurrence, so we need some initial values and we need some relationship between a term and the terms that come before it. So we're going to start with after 1 month. Maybe we'll say it like this. After 1 month, they're not 2 months old yet, so they haven't bred. They got there when they were 0 months old. There's just one pair of rabbits. At the end of the second month, they're still not 2 months old, so there's still one pair. And then at the third month, the end of the third month, the rabbits have produced a new pair, 1 plus 1, which is 2. Is this how we want to do this? Or should the recurrence be, okay. Yeah, so let's say they reproduce at the beginning of this month. As soon as they're 2 months old, which is a day after this, they reproduce. And so these rabbits are like almost a month old. They're like 29 days old. They're not quite a month old. We'll pretend. So next, what is a sub 4? This is going to be, well, we have the first rabbits, this one here, and they also produce another another rabbit, breeding pair. And then this one comes down, they're still alive, but they haven't reproduced yet. This is equal to 3. So what's going on? All of the rabbits that were alive are still alive, and the rabbits that were alive 2 months prior have another baby, is this idea. Okay, what about a sub 4, or sorry, a sub 5? This is our original rabbit lives. It has another pair. This baby that it had the previous month doesn't have another baby, but it still is alive. And this pair right here has now been alive for 2 months. It was born, at 2 months and 1 day, and now it's 5 months in, so it's over 2 months old, so it has another baby. And here we have 1, 2, 3, 4, 5 equals 5. Sorry, this was a 3 there. So we have 5 total. But what's going on? All of the rabbits that were around last month are still around. And all the rabbits that were around 2 months prior had a baby. So they've doubled. We've gained that many more. So we've doubled that number, and we have all the ones that we had before. Or we gained this amount. And we have this amount here. So in general, now let's look at a sub n. So we think that after n months, all the rabbits that were alive after n minus 1 months are still alive. Okay? So we have that many from the previous month. However, all the breeding pairs of rabbits, that were alive 2 months prior had new babies. Okay, So what does this mean? So it means that after n months, the number of breeding pairs of rabbits we have is equal to the number of breeding pairs that were around the month before, plus the number of babies by those that were at least 2 months old. So the ones that were at least 2 months old are the ones that were around n minus 2 months ago. Or sorry, just 2 months ago, which is in month n minus 2. So we add a sub n minus 2, right? And this is like old rabbits, or older, and this is our baby rabbits. Baby rabbits. And this is the total. Older rabbits plus baby rabbits is total number of rabbits. Okay, so now we have a recurrence. This defines a relationship between a sub n and terms that have come before it. And we need at least 2 terms to figure this out. We need only 2 months have to have gone by for us to look 2 months in the past, right? So this is true for n bigger than or equal to 3. This isn't true for the first 2 months. You'll notice that this recurrence can't go back to an a sub 0. So we need to figure out what the first 2 are, and then we can see that this is true. Notice that 2 is equal to 1 plus 1, 3 is equal to 2 plus 1, 5 is equal to 3 plus 2, etc. So again, so the recurrence is this relationship, and also a sub 1 equals 1, a sub 2 equals 1. All right. I lied to you, as I've done a couple times. This recurrence is not so underground. This is called the Fibonacci recurrence. Fibonacci recurrence. All right. And it is one of the more famous things that come out of math. So it's nice to have seen that here right before you. And this shows up in a few other places that we might see again. All right. So the question is here as follows, while I erase. Imagine that I have a 2 by n chessboard and a pile of 1 by 2 dominoes. So I'd like to tile, which means cover with non-overlapping dominoes, this chessboard with the dominoes. So the question is, how many ways can I do that? And this isn't really a chessboard, I guess. 2 by n would be a weird way to play a game of chess. Maybe you can find a way to do so. Okay. But so the question is that here we want to show that the number of ways to tile this chessboard satisfies the recurrence t sub n equals t sub n minus 1 plus t sub n minus 2. And notice this is the same recurrence as we had before. The new term is the sum of the 2 previous ones. Okay? All right. So we don't even need the initial conditions, but we can figure them out right now. Suppose that we have, when n equals 1, so for t1, we have a 2 by 1 chessboard. So we have a 2 by 1 board. Okay, that means I have 2 rows and 1 column. And I have to figure out all the ways I can fit a 2 by 1 domino here. There's only one way to do that. It's domino shaped already. So there's only going to be one right here. T2, this is a 2 by 2 board. Okay, so it's 2 rows and 2 columns. All right. And how many ways can I tile this one? Well, I can think, if I have a vertical domino here, I have to have a vertical domino there, so I can do one with vertical dominoes. And if I have a horizontal domino here, I can have a horizontal domino here as well only. So there end up being 2 ways. 2 ways. This was 1 way. Okay. So now let's think about, we have these first couple, but let's look at a general t sub n. So I have a 2 by n grid right here, or 2 by n chessboard. All right. So again, the power of recurrence oftentimes is we can use like a smaller subproblem and use our recurrence and have an understanding of the count there to relate it to a new problem. So here what we're going to do is we're going to notice that like smaller tilings of smaller boards or tilings of smaller boards can live within our tiling of this complete board. So what I want to do is I want to look at tilings, count all the tilings of this board size n in 2 ways. So number tilings of 2 by n chessboard. Okay, one of the things it's equal to is t sub n. right? This thing right here is defined to be the number of tilings of a 2x(n) chessboard. So again, in this double count, this is just a fact. 2x(n) is equal to this, or T sub n is equal to that. Another way to count them, I'm going to split them up based off what the tiling looks like at the end. I'm going to split it into two cases, and you can use the addition principle. I'm going to look at all of the ways to tile it with a vertical tile and with ending in a horizontal tile. And notice if you end in a vertical tile, that's like sort of in one way, but if you have a horizontal tile right here, you have to have a horizontal tile below it as well. There's no other way to finish the tiling. Okay? So I'm going to write this as number of ways to end a tiling with what I'm going to call it a vertical one is going to be a 2x1 domino, and then plus the number of ways to end tiling with 1x2 domino. So again, this sort of idea, this sort of splitting into cases is a really powerful idea, and we're doing a lot in this section on recurrences. We're counting something in two ways. We're saying that Tn should be equal to this, and this is also equal to some sort of partition cases. And we're going to translate each of these counts into things that we know based off of our recurrence relation. Okay, so if I end a tiling with a 2x1 domino, that means I have some sort of tiling that ends like this. So the last thing is a vertical domino here. But what comes before that? What comes before this last piece now? This right here, stopping before that, this is a 2 times n minus 1 chessboard. And it's fully tiled. There's 1x2 dominoes covering all of it. That's been fully tiled. So how many ways are there to have a tiling that covers a 2x(n) cross chessboard with a vertical tile? Well, it's all the ways to tile a 2x(n minus 1 board and then add a piece on the end in sort of one ways. So this should be equal to this thing right here, ending with a vertical domino, is just t sub n minus 1. So the next question is, how many ways are there to end a tiling with a 1x2 domino? Well, we know it has to be two 1x2s stacked on top of each other. Right? So over here, we have two 1x2s stacked on top of each other. But I'm again going to look at what comes before. This piece right here, this is a 2 by n minus 2 chessboard. And it's fully tiled. It's covered in these 1x2 dominoes, and it's completely covered. That means how many ways can we do that? There's t sub n minus 2 ways to tile all of this, and then we can smack down two horizontal dominoes at the end. So this should be t sub n minus 2. And indeed, this piece over here is plus ways to end a tiling with a 1x2 is t sub n minus 2. So what does that mean? Using my double count, this thing over here is equal to this piece over here. I'm still small. That's 2 sips. Okay. All right. So does that mean t sub n is equal to, tracing through this line of inequalities, or equalities, t sub n minus 1 plus t sub n minus 2. So what's notable here? So this shows what we want. It satisfies this recurrence, or this recurrence relationship here between t sub n and the previous term. But how is this different from the previous problem? These end up being like different sequences. The reason why this one will end up being different is because our initial values are different. In the previous problem, we had a1 equals 1 and a2 equals 1. But in this problem, we have a1 or t1 equals 1, t2 equals 2. So our recurrence also satisfies. So this is for n at least 3. And we also have t1 equals 1, t2 equals 2. So what are the first few terms of this? You can see it looks different pretty quickly. You have 1, 2, some of the previous 2, we can use the recurrence now, is 3. Some of the previous 2 is 5. Some of the next 2 is 8. Some of the next 2 is 13. Okay, this doesn't look too different. Everything is off by 1. The previous one had a pair of 1s at the beginning and then went through like this. This only has 1 1 to start us off. Okay. Cool. So this recurrence is, I guess, slightly differently, and I would claim this is a different recurrence because it has different initial conditions, but these two end up being quite similar in appearance. All right, people feel good. We've seen a couple of these things about Fibonacci. All right. All right. Okay. All right. I actually want to skip this one in the interest of time. All right. What I want to do next is find a recurrence for the number of binary strings of length n and the number of binary strings of length n without two consecutive zeros. So I think we solved the first one before, but we haven't shown it as a recurrence. And we also, now we'll look at the second one, we need to do binary strings of length n without two consecutive zeros. Did you solve that, Corey, or is this first time today?
No, I didn't solve
Cool, all right, first time today. Number of binary strings of length n, though, is just an oldie but a goodie. So we'll do just length n.
that. I have, that's been solved multiple.
Yes, length n. This is, and to some extent, this is one of the best things to come away with in this, from this, this sort of marathon. It's a powerful tool. Binary strings are super, super flexible because they tell you it's a yes or no question. And so oftentimes you can change a complicated problem into a bunch of yes or no questions in order. Okay, so number of binary strings of length n. I'm just going to call this b sub n is going to be number of binary strings of length n. Binary strings of length n. B is for binary, n is for n. Okay, so what do we have first? What is b sub 1? This is the number of binary strings of length 1. So I have one spot, and I can pick two things to be here. So I have two options. So it's 2 to the power of 1, just 2. Okay? Next we have b sub 2. Maybe you can see something. We have two spots. I have two options. I can put a 0 or 1 here. So I have two things I can do. Two options here as well. So this ends up being 2 squared, which is 4. So we see a couple. We don't actually need more than one term for this recurrence, but it was just nice to see, I think, to get us started. Let's see in general. I want to figure out b sub n. And so I want to think about, again, a double count, number of ways to make a binary string starting, sorry, not starting, binary string of length n. Okay, and I want to count this in two ways again, as I'm going to do a lot in recurrences. So on the left, I'm going to count it as b sub n. This is just a definition. I know that this is defined to be this number, so that is just the number of ways. So one way to count it is just as b sub n. All right? And then what I'm going to do is I'm going to look at this as being split off into cases, if we want to, based off what the first digit is. So the idea is equals, we have our one digit here, or one number, and then we have a bunch afterwards. So I'm going to split this into cases based off what this first thing is. Then I'm going to notice that what follows is a binary string of length n minus 1. So I'm going to be, should be equal to, this isn't necessarily correct as a line of equality. So it should be the number of binary strings of length n starting with a 1, plus the same thing starting with a 0. So I split this binary string can start with a 0 or 1, so I split it off into all the cases. I'm going to count each of these. I'm going to count the first one. How many binary strings start with a 1 of length n? So I know this is a 1, so I have one option to put here. And then I have two options for each of the next ones, right? Put anything here. This right here, you'll notice, and indeed, this is a binary string of length n minus 1. This is a binary string of length n minus 1. N minus 1. So this number right here should be equal to, I can take a binary string of length n minus 1 and chunk a 1 on the front, and we should be good. So this should be equal to b sub n minus 1. Again, this counts how many ways to have a binary string of length n minus 1. Now let's figure out all the binary strings that start with a 0. So I know I have a 0 out front, and I have a bunch of things that follow, but again, this is just a binary string of length n minus 1. Binary string of length n minus 1. Okay? So how many ways can I fill out a binary string of length n minus 1? That's b sub n minus 1, and I chunk a 0 on the end. So this number of binary strings satisfying this condition should be b sub n minus 1 as well, which is 2 times b sub n minus 1. Okay, so what does this mean? This means that b sub n, the number of binary strings of length n minus 1, is equal to twice the number of binary strings of length n minus 1, twice the previous term in the recurrence. So the first term is equal to 2, next one is equal to 4, and in general we have b sub n is equal to 2 times b sub n minus 1 for n greater than or equal to 2, and the first term b sub 1 equals 2. And one can, as was mentioned before, one can find a closed form of this, and if you do, you end up finding that b sub n is 2 to the power of n, if you wanted to. That's a little outside our scope today of finding closed forms for recurrences, but perhaps a curiosity.
Well, surely not that one specifically.
Pardon?
Surely not that closed form specifically.
Certainly not that closed form specifically, yes. This one is not, every single time. If it was just the,
Find them, yes.
yes.
Yeah, this one,
This one, yeah.
use camera.
Yeah. But it is something I do find in math, oftentimes the easiest way to solve a problem is to already know the answer. And I think this is certainly one of those situations where maybe you already knew that answer. Easiest way to find the closed form was to do so.
Nathan was really good at that in one of my classes. He'd be like, oh yeah, the closed form is this. I'm like, how did you know that?
Yeah. You just already know.
He just saw it, he just saw it.
All right. So let us design a flag with n stripes of color red, white, or green, which are, I don't know if people know this, those are the colors of the Hungarian flag, such that two adjacent strips or stripes never have the same color. Moreover, we forbid the top and bottom strip to have the same color. Find a recurrence and the initial conditions for L sub n, the number of such n stripe flags. Okay. So we're going to do the things we've done before. We're going to use a couple terms of our recurrence. I know how many we have to because I've done this before. And then we're going to try to solve the problem in general, and we're going to do so using our double count. Okay. So what's L sub 1? This is we have one stripe, and we're calling it in one of three ways. So how many ways? How many ways can I color this red, white, or green? Daniel, you know? 3, nice.
Not honest, you walk in and ready to go. Nice.
Okay, cool. So there's 3 ways to do that. What is L2 then? I have 2 stripes. I claim I have 3 colors I can pick for this top one, but I can't pick the same color for this stripe down here. So it ends up being 2 for this. So it's 3 times 2 equals 6. Maybe you have L3. You can sort of see what's going on. Okay. And I'm going to do something a little different. I claim I have 3 colors to pick for this top line. Pick that in one of 3 ways. But I'm not going to go to this next thing here. I'm going to notice that, hey, the bottom line can't be the same color as the top. So if this was green, this can't be green. So I'm going to pick the bottom one in one of 2 ways. Okay? And then I'm going to say, all right, well, this is like, for instance, red, and this is a different color, maybe green, and this middle stripe has to be different from the one above and below. This ends up just being 1 way. This is actually also 6, interestingly enough, I think. What I want to do now is solve this in general. So I'm going to let, in the middle, I'm going to do a recurrence relation. So for L sub n, I'm going to do number of ways to color an n-striped flag as directed. And by as directed, I mean I just don't want to write out the whole problem. This is saying number of ways to color an n-striped flag such that the top is different color than the bottom, no 2 adjacent stripes are the same color, and also that every stripe is colored one or red, green, or white. So on this side, I'll have it be, I'll break it off by, this is just going to be L sub n. This is always the easy part of our count, the definition side. And then over here, I'm going to split it off based off of if the second from the bottom stripe is the same or different color than the top stripe. Maybe isn't the most natural way to break things off. But what's going on, maybe I have something, I have some flag here. Okay. So in this setting, this right here, so maybe the top, suppose the top is green. The bottom one can't be green, right? This one right here is either red or white, okay? And this one right above it can be either red or white, the other color the other option here, but it could also be maybe white, red, or it could be green. So the question I'm asking is, one case is where the top is green and then the second from the bottom is green, or maybe the top is red, second from the bottom is red, top is white, second from the bottom is white. The other case is where the top is one color and the second from the bottom is a different color. And this might seem like a weird way to break this count down, but it ends up being sort of what we want to do in this problem. So I'm going to break it off into cases based off of the color, or if the color is the same or different as the second from the top. So I'm going to look at the case first where it's the same. Okay. So I have this flag right here. All right. So this is one color. I have a bunch of stuff going on. Okay. And what I'm going to notice is that, okay, so this is the same. So this is like color same, or maybe this is like green. Maybe this is also green. Okay. And this is either, if that's green, this is not green, this is red or white. Right. All right. So when I look at this, the key insight is that this region, I want to look at this piece right here. The flag, the first n-2 stripes of this flag right here. The top is like some color, maybe it's green, could be something else. The next one below it is a different color, then the one below that's a different color, one below that's a different color, one below that's a different color. And the one just above the n-2nd one has to be a different color than green, because two adjacent stripes can't be the same color. So this has to be something that's red or white. What that means is that this flag right here, the top n-2 rows, satisfy the conditions we need. Adjacent strips are different colors, the top and the bottom are of different colors. That's sort of our main idea. So that means that we can color these things in one of L sub n-2 ways. So this is going to be L sub n-2 ways to make this. Make this happen. We can color that. And then the rest of it, this row right here has to be the same as the top one, so we can pick the same color as the top row in one of one ways. So we'll multiply by 1 times 1, and then this row down here has to just be different from the top and the second from the bottom. So there's two ways to pick a color here. For instance, if this was green and this was green, this one could be red or white. So we have times 2. So based off the same, this should be L sub n minus 2 times 2. 2 times 1, really, we have going on here. Okay, so next we'll look at the different case. So now different. Diff will be short for different. All right, so here we have, okay, we have a flag right here. All right. In this case, in this setting, here, right, so this is maybe this was green, maybe this is red or white. The bottom row also has to be red or white, but it has to be different than the one above it, so maybe we'll call it white or red. All right. So my observation here is that now I'm going to look at the first n minus 1 rows. We start with one color, we end with a different color, ignoring the bottom row. And in the middle, we have no two adjacent rows of the same color, right? Because it has to be a valid flag. So there's L minus n, L sub n minus 1 ways to make this happen, go from green to red or green to white. And then after you do so, when this is red or white, the other color is determined for this bottom row. If this one was red, the bottom one has to be white. And so then there's one way to fill it out. So you can do the first n minus 1 rows in however of the L sub n minus 1 ways that you had before, and you fill it out in exactly one way. So then there's L sub n minus 1 ways total ways to make this happen. Make this happen. All right? So our double count, we've partitioned now, I didn't write it explicitly. We wanted to split our count into colorings in which the second from the bottom row is the same as the top. And we could do that in 2 times L sub n minus 2 ways. And then we're adding the ways in which the second from the bottom row was a different color from the top. And there were plus L sub n minus 1 of those. Cool. What am I missing? I think I might be missing something with this. This is a little bit off, but this is definitely the recurrence right here. L sub n equals 2 times L sub n minus 2 plus L sub n minus 1. And I think I might have gotten a little bogged down in this one right here. This count might be wrong, but we'll just ignore it. Pretend it never happened. Perhaps someone could figure that one out for me. See where I was led astray. Cool. All right. Let's go a little further. We can go on to the next one unless there's any questions. Okay. So the problem is, find a recurrence for S sub n, the number of subsets of an n element set. I hear this is the closed form people are going crazy about. Okay. So recurrence for S sub n, the number of elements or subsets of an n element set. What is S sub, we'll call S sub 1? How many subsets are there of a one element set? Well, you can either have, maybe for instance, if we just have the set 1, you can either have 1, or you can have the empty set. 2 ways. S sub 2 is going to be, we have a 2-element set, so we have the set itself, set containing 1, set containing 2, and the empty set. So the count is 4. And you can continue on like this. You can enumerate them as follows. But we're going to do so with a double count right here. So in the middle, I'm going to have number of elements of an n, sorry, number of subsets of an n element set. Count it 2 ways. One way we'll count it is as S sub n. That's just sort of the definition of S sub n. And in the other side, we're going to think of it specifically being the n element set. We're going to think of the set 1, 2, 3, up to the number n, as we often like to do. But it really doesn't matter. You can think about any n element set. So here, what I'm going to do is I'm going to break this into 2 cases based off of, I'm going to count all of the sets that contain the number 1 and all of the sets that contain the number 2. Or sorry, sorry, not that contain the number 2. All the sets that contain the number 1, all the sets that don't contain 1. So it equals sets containing 1, and plus sets not containing 1. Okay. Okay, so what do I want to notice? Maybe instead of containing 1, let's actually look at sets containing n. It might make our count a little bit nicer to go through. So sets containing element n, or the sets not containing element n. So let's count first the sets containing n, or subsets containing n. What's this going to be? So what does that look like? What does a set or a subset of these numbers containing n looks like? It looks like, these look like a subset of 1, 2, 3, all the way up to n minus 1, together with n, right? So the idea is, how do I make a set or a subset of these things containing n? Pick all the things less than n that you want to be in there, and then add n onto it. Those are all the ways to do so, okay? So there are, you'll notice that there are, how many ways can I take a subset of 1 up to n minus 1? So there are s sub n minus 1 ways to do this. All right? And now let's count sets not containing n. Sets not containing n. Okay. So what does a subset of the numbers 1 up to n look like that doesn't contain n? This just looks like a subset of 1 up to n minus 1. These look like subsets of 1, 2, all the way up to n minus 1. How many ways are there to find a subset of that? That just looks like there are s sub n minus 1 ways to do this. Okay. So what is this? How many sets or subsets of this thing contain n? This should be equal to s sub n minus 1 plus the number of subsets not containing n, which is s sub n minus 1. So combining this piece right here, and this section right here, we have s sub n is equal to 2 times s sub n minus 1. And that's together with this notion that we only need one term in our recurrence. This is for n greater than or equal to 2, and we also have s sub 1 equals 2. We have seen this earlier when we counted the number of binary strings of length n. we had the recurrence S or B sub n equals 2 times B sub n minus 1, and the number of binary strings of length 1 was also 2. So this is going to be the same recurrence. We have the same initial condition. We have the same relationship, so the sequences will be the same. The reason why is that there's a really, really nice connection between binary strings of length n and subsets of an n element set. Cool. We'll go big. Nice.
I'm not on top of it either.
That's fine. We're not even to scary hours yet. All right, we'll erase small and we'll go on to the next slide. All right. But on top of that, I really feel like this is sort of nice. This is one of the nice things, I think. It's nice to do what you enjoy. I feel like I'm given strength by all of these awesome problems. Towers of Hanoi is a classic. I remember being so jazzed about it when I learned about it as a wee younger person. And I'm still excited about this sort of idea. Again, so there's I think this problem, especially, is sort of this physical problem that maybe people have seen before, but it really encapsulates the sort of thing that is going on with recurrence, and we'll see a little bit later on in the next section presented by Corey. This really, really powerful idea of we're relating a problem that we already know how to solve, and then we look at a slightly bigger problem, and we use our previous understanding to relate to something bigger. Okay, so the Towers of Hanoi puzzle consists of 3 pegs. Let's sort of try to draw a picture of this. All right. With n disks of decreasing size placed on the first peg. The goal of the game is to move all the disks to the last peg. So at each step, specifically, the player is allowed to move 1 disk to another peg as long as the disk is never placed on top of a smaller disk. So maybe we can draw some pictures. Maybe we have big one here, and a slightly smaller one above it, then a baby one here. You can take a step. One such step would be to move this small ring. This is with n equals 3, by the way. You can move this small ring onto here. I'm going to now draw something that's not allowed. I can't take this piece right here and move it on top of the smaller ring. That's exactly the thing that's not allowed. You can't take a bigger piece and put it on top of a smaller piece. So after I move this one over, the only next thing I can do, I can either move my small piece or I can move my middle piece over to here. Would be an allowable second move. So these are the things I can do. And so the next question will be, suppose I have all my pieces on the ring on the left and I want to move them to some ring maybe on the right or maybe in the middle. What's the fewest number of moves it'll take me to do so? Okay. So I'm going to let h sub n be the minimum number of moves needed to win the puzzle with n disks. So again, the puzzle is I have a stack of n disks, and I want to move on the left one, and I want to move them all the way to the right. So I want to come up with a recurrence needed to win the puzzle with n disks. Or come up with a recurrence for h sub n in terms of h sub n minus 1. So what is h sub 1? I'll do this one first. This one's kind of nice. I have 3 pegs. I have 1 ring on this peg. And I need to figure out the fewest number of moves to move all the pegs from the left peg to the right one. This is actually just 1. I just move the peg, or move the ring over. So it's 1 move. Right? Not so bad. Okay. We can look at some more, but now I'm just going to look at h sub n, right? And I want to think about all the minimum number of ways to move h sub n. So what happens with, I'm just going to look at h sub n, we might not really do a double count here. Okay. So we have 3 pegs here, and I have a whole stack of n of them getting smaller and smaller. Smaller right here.
Yes.
Easy. Take a sip.
We got a lot of people. There's like 23 people in there. Yeah. No, it's not bad.
It's 22 of my alts. All right. So the first thing is, suppose we're going to move each of these over in the fewest number of ways. I'm not going to tell you exactly how many ways there are to do that, but suppose we move them all over to here in that number of ways. If we move all of these pieces, if all of the rings on this peg right here are going to move over there, I claim at some point the small or the biggest ring has to move, right? The biggest ring, if all the rings move, the biggest ring has to move. Okay. And so what happens? So the biggest ring will be over here. It can only move if it's the only piece right here. And the only way it can move over here is if there's no smaller things beneath it. So when can the biggest ring move? There's a unique arrangement that we can get to when the biggest ring can move. Okay, so it's allowed to move when it's the only piece right here, the biggest one. It can't move on top of a smaller ring, but all the rings are smaller. So there can't be anything on this peg. That means all of the rings 1 through n minus 1 have to be on this peg. And if you have all of those on the same peg, there's really only one way that those can have been arranged, right? So those all have to be around here. They have to be in also size order. So it doesn't really make sense at the top there, but we're fine. Okay. So the fewest number of ways for me to have moved all of these pegs over to this middle one was h sub n minus 1. So I could have done this. Like I need at least h sub n minus 1 moves to get here. Get here, right? H sub n minus 1 is the number of ways to take the n minus 1 rings that are stacked above and move them all in order onto another ring. So that's counted by this thing right here. Okay, so at this point right here, what's going to happen next? Well, the only thing I can do is I can move this small one over, but I probably wouldn't do that. I want to move my big ring. Okay, so when I move my big ring, I go to this arrangement. The peg on the left is empty. The middle peg has like an n minus 1 tower. And the peg on the right has my biggest ring. Okay? So that means I took one move. And now I want to rearrange this stack right here so that it's all on top of my biggest ring. So how many ways can I do that? Like how many moves does it take to do that? Well, this is an n minus 1 stack, and I need to move it to another peg. So to get to the following arrangement, empty peg, then I have peg with a really big one, and then the n minus 1 rings above it. It's going to take me another h sub n minus 1 moves to do this. Need another h sub n minus 1 moves to get here. Here, right? So I moved these pieces onto this stack over here. So what does this mean? And the idea is you need at least this many, and it's also quite possible to do so. I'll leave this for another time. So what does this mean? This means that h sub n should be the fewest number of ways to get to this arrangement, which is h sub n minus 1, plus 1, moving the big ring, plus 1, plus the number of moves to get to this arrangement, which is h sub n minus 1. I'm going to combine like terms, and you get h sub n equals 2 times h sub n minus 1 plus 1. This is for n greater than or equal to 2. So recurrence is this combined with our knowledge of h sub 1, which is 1 move. H sub 1 equals 1. Awesome. Okay. Sounds good. Questions there? People feel okay? Awesome. Go to the next one. I'm going to go big. I have a low battery microphone, so I'm going to switch, but we can have a nice look at this picture without defining it.
How do you know it's low battery? Is it flashing at you?
Because it says there's a red battery sign on it.
Oh, okay, cool.
Yeah, that's my intuition.
This one seems to be full.
Yeah. Fine, we'll do some rearrange. Move this back. Perfect. Like it never moved. All right, back in action. So we need a binary or a recurrence relation for B sub n, the worst possible runtime for a binary search on a sorted list of n numbers. So to do this, we have to talk about what binary search is on a sorted list of n numbers. All right. Grab a new pen. So suppose I'll just do this with one example list of numbers, and maybe they'll all be different. So maybe this is like 1, 2, 5, 7, 9, 10, 12, 15. This is my list. And this is a list of 1, 2, 3, 4, 5, 6, 7. We'll do 9 pieces. Wait, that's not sorted. A ninth thing, number 17. Okay, so this is sorted. And my goal of binary search is I want to find a number that I know is in my list, and I want to search for it, or maybe if I want to see if it's in my list. So what I want to do is I want to look for the number. Anyone have a number they want to look for? 2? Good number. Okay, so here's what I do in binary search. What I do is I look at the middle value of whatever I'm considering. And so this is called like a recursive process. So I have my list that's sorted, and I want to look at the middle value. So I want to look at 1, 2, 5, 7, 9, 10, 12, 15, 17. So 9 is the middle entry. There's 4 to the left and 4 to the right. If there's a tie, you just pick one at random. Okay, so I'm going to notice 2 is less than 9. It's not, if it was equal to 9, we'd be done. We'd say, hey, I found it, you're good to go, you're golden, you got this really quick. 2 is less than 9, however. But what does that mean? Well, 2 is less than 9, and this list is sorted. So I know 2 is somewhere in here, I think it is. It can't be to the right of 9, though, right? Because it's, all these numbers are bigger than 9, and 2 is less than 9. So it has to be over here. So I throw away 9 and above. So now I just look at, now I'm going to look for 2 again, for 2 in the list. 1, 2, 5, 7. And here I look at the middle and I break a tie randomly. So if I pick below, I get the number 2. But if I pick above, I pick 5. Or maybe you don't always pick randomly. Maybe you always pick the higher one if there's a tie. I think random is bad here. So we'll say we always pick the bigger one. So say we pick 5. 2 is less than 5. So we're going to throw away 5 and above, and we're just going to have 1 and 2. So now we just have 1, 2. I look for the middle that's right between these two values, and with my new approach, I'm going to pick the bigger one. So that means I have 1, 2, and I've picked 2. That's messy. So now I've found 2. Okay, so I remember, I know what this position is, and if I've done this process, I can actually isolate exactly what position in my list this thing was. If I do keep careful track with powers of 2 going on. But the idea is, okay, so worst possible runtime means the most possible steps that happen as I go through here. The best possible runtime is if it's right in the middle and I find it immediately. So the best possible runtime is 1. Worst possible runtime will be the most number of these sorts of searches I have to do, searches and divisions. So let's look at this. Okay. So I'm going to keep this. Suppose I'm always, again, tie breaking by picking the bigger number. So what if I have, no, I'm big. We're good. Okay. B sub 1. This means I have a list of one number, maybe it's the number 1, and I want to search this for 1. I claim that I'll be able to know in one search. Just need one search. Okay, so this is going to be 1. B sub 2. B sub 2. Here I have maybe two numbers 1 and 2. And let's suppose I'm looking for the number 1. Look for 1. The idea is, what I'm going to do is I'm going to look at the middle and go to 1 higher. So I have 1 comma 2 here. If I was looking for 2, I'd be done. If I was looking for a number less than 2, I would throw this away, and I would look right here. And so I would say, okay, now I have a list of length 1 in it here, and it took me 2 times to find this. So again, I found it after 2 searches. 2 searches at worst. Okay, so this was equal to 2. All right. So now what happens if, let's look at this. Now consider a general B sub n. So I have some list of n numbers right here. All right, that are sorted, and I search for them. So I look at the middle value, all right, and then I throw away everything else. I say, okay, if I find the number I'm done, I'm looking for something else. If the thing I'm looking for is bigger than this, throw away this and everything below. If the number is smaller than this, throw away this and everything above. Okay, so suppose it's smaller, right? I throw this piece away. This number right here, if this is a list of length n, the whole thing is a list of length n, this is like the floor of n over 2 entry, right here, right? So you split a tie, you go above, so this is the floor of n over 2 to the left right here. Okay, so now what I'm going to do is after this point, I search again, but now I again just have a sorted list of length n minus 2. Next step, we search a sorted list of numbers of length, floor of n over 2. Okay, so if I have a sorted list of length n over 2 or floor of n over 2, this is an integer, right? The worst possible runtime to do this, at worst, we do this in capital B sub the floor of n over 2 steps. Right? That's the worst case runtime. So either we find it here, and if it keeps going really bad, it takes this long. So what does this mean? So we did one step to divide it in half, and then we got it into terms of something that we already knew. So this means that B sub n, worst possible runtime is 1 plus worst possible runtime on a list of length n over 2, plus B of floor of n over 2. Okay. So this is a recurrence. As it turns out, so this thing here is something about the size of like half the recurrence. It's just one more. This ends up growing quite slowly. This actually grows, it's called logarithmic growth. And so this is kind of quite nice. And so closed form ends up being log n for this sort of thing right here. Cool. Worst possible runtime. Whoa, it's yellower. I don't know what happened. We will persevere. Okay. Oh, it's the computer I see. It's in blue light reduction. Okay.
Stream looks fine.
That is good to hear. Okay. I'm going to hide myself for a second, show the problem. For the following problem, we consider the following. We're going to write the natural numbers 1 through n in a circle. We're going to start at 1, I'm going to cross off every other number until only one number is left. I'm going to let j sub n be the last remaining number. I'll show a couple examples of these in a sec. You don't have to exactly know what's going on with that. So the problem is called the Josephus problem. This is a famous problem. We're going to prove that j sub n satisfies both of the following recurrence relations. And so they're different based off of the parity of the term. So j sub 2n, so that's j sub an even number, is equal to twice j sub n minus 1. And j sub 2n plus 1 is equal to 2 times j sub n plus 1. And this is for n greater than or equal to 1. Okay. Here we go. I'm huge. So let's look at what's going on for this. So what is j sub, maybe j sub 1 doesn't make a ton of sense because there's only one person, they're the only one remaining. J sub 1 equals 1. So the idea is one person sitting around in a circle, you cross off every other till only one person's left. They're done. J sub 2, I'll explain. You have two people sitting around in a circle. So again, isn't that interesting? You start at 1, you cross off the person next to them, that's person 2. This person remains. So j sub 2 equals 1. All right. We can look at j sub 3. So you have 1, 2, 3 sitting around in a circle. Start at 1, cross off the next person, go to the next person still around, cross off the next one. 3 is the last person remaining. J sub 4 is equal to, so we put 1, 2, 3, 4 around in a circle. Start off 1, cross off 2, go to 3, cross off 4. And now, once you get crossed off, you sort of move back in the circle, I think we'll say. So now we've crossed off 4, we go to 1, and then the next person is 3. So we cross off 3. So that's, last person remaining is 1, so this is going to be 1. So this is the general form of what's going on. The idea is, again, we start at 1, we cross off the next person, go to 3, cross off the next person, and once you come back around, everyone else has moved back. So once you've been crossed off, you step back, and we just play again where we played this. After 2 and 4 were crossed off, we played with 1 and 3 remaining. Okay, so what we can do, we can establish these recurrences in general for j sub, I'm going to first do it for j sub 2n. Suppose I have 2n people sitting around in a circle, which is an even number. Okay, so the first time around the circle, all of the even numbered, okay, all right, all of the even numbers, so I'm going to make sure I'm sticking with my phrase in this problem, all the even numbers get crossed off, right? 2 gets crossed off, then 4, then 6, then 8, all the way up to 2n. And they all bow out, and all you have remaining is the odd numbers. And so you have all of them kind of get closer in the circle. And they play the game again, just starting with the number 1. The person to the left of them gets crossed off, and then 2 more gets crossed off, and you keep going around. So what does this mean? So after this, with j sub 2n, we play again. Again with n people, where the kth person in order was originally in position 2k minus 1. In position 2k minus 1. So I think this is a little involved to look at. This is a simple picture though. So the idea is you have 1, 2, 3, 4, 5, 6, maybe 7, 8, 9, 10, 11, 12, like a clock. And so at first you cross off, I'll move the 1 a little bit, cross off 2, cross off 4, cross off 6, cross off 8, cross off 10, cross off 12. And now 1 is in the first position, 3 is in the second position, and you notice that, so here 2 equals 2 times 2 minus 1. So here when k equals 2, they were originally in position 3. Here the third person was in position 5, so it's 3 times 2 minus 1. The fourth person was originally in position 7, 4 times 2 minus 1. Position 5 was originally 5 times 2 minus 1, 6 times 2 minus 1. So this goes around. So then we just play the game again with them. So we play the game with n people, with the person who won was, or the kth person in order was originally in position 2k minus 1. So then, who is the winner? The winner is number j sub n in this new game. This new game so j sub n of the n people, but they were originally in position, whatever this number is, times 2 minus 1, was in position 2 times j sub n minus 1. So what do I mean by that? I'm saying, hey, so we've crossed out half the people, maybe in this case it was 6, and we just have the odds remaining. And say, okay, suppose if I know that if I have 6 people around here, that the person in the third position wins, or the number in the third position wins. Okay, well what does that translate back to in our original numbering? The third position in the new game is the 3 times 2 minus 1th position in the original. So the third 1, 2, 3 is 5. So this is again a complicated way to phrase this sort of go-between after you remove the odd numbers, how do you connect the kth odd number is 2 times k minus 1 is sort of the idea here. So this is the person who wins. All right. So now we'll figure out what is j sub 2n plus 1. This actually isn't too much more involved. So the idea is here, j sub 2n plus 1, cross off all the even numbers, then 1. So what does this look like? Suppose we had now we have an odd number of numbers around here. Yeah, odd, okay, that works, odd number of numbers, yeah. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so I start at 1. What I'm prescribing here, cross off the even, cross off the next even, cross off the next even, cross off the next even, and then come back just past my starting point, cross off 1. So here, I have 9 numbers, and 9 equals 4 times 2 plus 1. So we're looking at here a case with n equals 4. After this, how many numbers remain? So I've crossed off n many evens and 1 odd. So n odds remain. I have 3, 5, 7, and 9. So what I can think about is starting this go around, starting with 3, and then crossing off 5, and then going to 7 and going to 9. So I'm again just playing the Josephus game with n numbers, starting at 3. So again, as we play the game again with n people, we play with n people, where the kth person in order was originally in what position? Okay, so the first position is, so in the new game it's position 1, and they were in 3. Second position was in 5, which is 2 more. Third position was in 7, which is 2 more, so it ends up being in position 2 times, I'm skipping ahead. They were in position K, so they are in position K, so they were in 2 times K plus 1. This is just a re-indexing thing. This is my new first player. They were in position 2 times 1 plus 1. This is my new second player. They were in position 2 times 2 plus 1. This is my new third player. They were in position 2 times 3 plus 1. This is my, yeah, we don't have to go anymore. So the winner is J sub n in this new game. I have n players. So whatever J sub n, maybe the third player wins. And their original position was 2 times that value plus 1. So the winner is in position 2 times J sub n plus 1. Okay. So what does this mean? This means that J sub 2n plus 1, the position of the original winner, is equal to the position or of the winner of J sub n times 2 plus 1. So these things are equal to each other. Similarly, we have that J sub 2n is equal to 2 times J sub n minus 1. So our recurrences are satisfied for n greater than or equal to 1, which is awesome. Cool. Questions on that one? Feel good? Feel good? This is, yeah, I refer to this a couple different ways. Sort of got bogged down. This is sort of an artifact. This is the game that has been played with people before, and so oftentimes you think about people in a circle, and then maybe bow out for some value of bow out. But here we played it with just numbers. So that was the translation, but with this one. So if I refer to the numbers as people, I didn't mean to. And if I refer to the people as numbers, I also didn't mean to. Yes. I guess this is where it starts to get deranged again. Okay, my picture's big. Press the next button. What are we doing on time? Okay. I'm going to prove the following recurrence for the number of derangements d sub n. So we talked about derangements a while ago. This is where it gets more deranged again. Okay, so the following recurrence here. So d sub n, the number of derangements of a set of size n, so these are permutations that don't fix an element, should be equal to n minus 1 times the sum of the previous two terms. This is for n greater than or equal to 3. All right. Okay. So what I want to do is show the following. D sub n equals n minus 1 times d sub n minus 1 plus d sub n minus 2. All right? Okay. So what I want to do is figure out the number of ways to do derangements with a double count. So count number of derangements of a set of size n. Okay? And one way I'm going to count that is d sub n. As I have been, I'm going to have something over here that maybe translates to this given problem. And what I'm going to do is I'm going to break it down into cases based off of, first I'm going to look at where person 1, or whose hat person 1 gets to. So this is derangement, and so maybe you can think of this as being ways to give people their hats back. And so I'm going to split it off based off of, okay, hat that person 1 gets. So the question is, how many possible hats can person 1 get back in a derangement? Does anyone know, anyone remember? So this is like a hat check problem. There's n total hats. They all get given back to people, and no one gets their hat back. So person 1 had a hat. They don't get it back. They can get a hat back then in one of n minus 1 ways. So here, I'm going to look at this. Person 1 gets a hat back in one of n minus 1 ways. Okay. This n minus 1 here should be reminding us of this thing right here. Okay. So after they get their hat back, so we have all these different cases based off of which hat they get, and then we split into 2 more cases. Split into 2 more cases. Subcases. Okay. So first off, I'm going to ask the question, person 1, we're going to say they get hat I. So maybe say they get hat I. Person 1 gets hat I. Okay? The question is, whose hat does person I get? So one case will be person 1 gets hat I, and person I gets hat 1. So they just have their hats swapped back and forth. So one case will be one person I gets hat 1. And the second option will be person I does not get hat 1. All right, so those are the 2 things that can't happen. This is what we're going through with. So if person I gets hat 1, they've swapped hats. So there are n minus 2 other people and n minus 2 other corresponding hats. And so this can happen, this one right here, this can happen in one of d sub n minus 2 ways. Why? Because this is a derangement of the other n minus 2 people's hats. These 2 hats aren't fixed, so we kind of accounted for these 2 people first, and then we can think about the remaining people as being their own set, who got their hats all jumbled up. So none of the points are fixed, it's counted by d sub n minus 2. Okay, so if we're in the case of person 1 gets hat I, there's d sub n minus 2 ways for person I to get hat 1 in return. Next, we have to figure out person I doesn't get hat 1. Okay, so they get some other hat. All right, or sorry, so they get some other hat. Hat I is out of the picture. Hat I is out of the picture. And we can think about, well, what if we were to give person I hat 1? We can think about that is going to like replace this idea of a fixed point. Instead of having them not getting hat 1, we can like relabel it as hat I in a fake fun way that we're going to just allow to be true. So the other ways to do this, number of ways to do this is d sub n minus 1. And the idea is that all of the n minus 2 other people can't get their hats back, and person I can't get hat 1 back. This is very, very similar in flavor. In fact, it's exactly the same as, because their hat has been removed, you have having n minus 1 people and not being able to return their hat to them. Okay. So corresponding, we have n minus 1 ways to pick a hat to give to person 1, and we're going to multiply that by the number of ways that we can complete the derangement, which is d sub n plus 2 times d sub n minus 1. Okay? So it should be n minus 1, and again, that's just the hat that person 1 gets, that person 1 gets, times d sub n minus 2 plus d sub n minus 1, which is the number of ways to complete the derangement. The derangement. So using our double count again, we have d sub n is equal to n minus 1 times d sub n minus 2 plus d sub n minus 1, proving the recurrence. Cool. All right. Making good time. All right. We'll go big while I erase. I'm actually going to skip this one. There's a typo in it. That's just the way of these things. But what we did figure out, it's missing an n factorial minus at the beginning. But the thing that was stated is just strictly not true. Okay. I'm going to prove this problem, but I'm actually going to use the previous recurrence we just found. So I'm going to rewrite that, small and in the corner. D sub n equals d sub n minus, equals n minus 1, n minus 1 times d sub n minus 1 plus d sub n minus 2. Okay. All right, this is sort of a fun one. I need my notes. Okay, so we're going to do an algebraic proof of this because there's a way to do this with a double count, but it isn't very fun. And it's maybe beyond the scope of a discrete math class. I'm going to get a fresh pen as well. Get my writing hand. We got plenty of pens. Okay. So I'm going to start with, I'm going to need this space over here, and then that space over there as well. So I'm going to say something about n times d sub n minus 1 minus d sub n. All right. This is equal to n times d sub n minus 1. And then what I'm going to do is I'm going to replace this term d sub n with what I already know it defined by a previous recurrence. I'm going to set this to be equal to, so minus n minus 1 times d n minus 1 plus d n minus 2. Right. People see what I've done so far. I just started with something. I wrote this thing over here. I'm going to star it because it's going to be something I consider for a while. This thing, whatever it is equal to that first term minus, I replaced d sub n just with something else I know. Totally legal algebraically, because I have this equality. Okay. What comes next? That's a good question. I have some copies of d sub n minus 1 here, some copies there. I'm going to rewrite this. We have n d sub n minus 1 minus n minus 1 d sub n minus 1 minus n minus 1 d sub n minus 2. Okay? I have n copies of this thing here. I'm subtracting n minus 1 copies of it. And so you're left with this being equal to d sub n minus 1 minus n minus 1 times d sub n minus 2. Okay. So notice how this looks kind of similar to what we had before. We had an n, something one less, and then an n. We have an n minus 1. Wait, is this what I want to have here? Yeah, it is. Okay. So this is different by a sign. This ends up being, here we have an n minus 1 next to an n minus 2, and then an n minus 1. Here we have an n next to an n minus 1, and then an n. So these all sort of get decremented, but the signs are of different. Here this is negative, this sort of. There's a relationship between here. I'm just going to star it because it should look fishy to us. Okay. What does this recurrence also imply? One thing that we can do, this is true for all n, really that's greater than or equal to 3, and so this should be true also for all n greater than or equal to, we should have d sub n minus 1 equals n minus 2 times d sub n minus 2 plus d sub n minus 3. Okay, for some big values of n. All right, same recurrence, but I've just replaced every time I had an n with an n minus 1, still holds true, and then you simplify and you get this thing out. Okay, so using that, I can replace my d sub n minus 1 with this piece right here. So I'm going to write this as n minus 2 times d sub n minus 2 plus d sub n minus 3 minus n minus 1 times d sub n minus 2. And I'm going to do something, get some color going on, get some movement, get some blood flow. Here, I want to specifically highlight that I replaced d sub n with this piece. Here, I want to specifically highlight that I replaced d sub n minus 1 with this piece right here. All right? So next, I'm going to just expand and rearrange again. Okay? This should be equal to n minus 2 times d sub n minus 2 plus n minus 2 times d sub n minus 3 minus n minus 1 times d sub n minus 2. Okay? I've just distributed this n minus 2 out. I should have the same thing everywhere else. And here I have n minus 2 copies of d sub n minus 2, and I subtract off n minus 1 copies of it. So you have something, maybe this is like 6, and I subtract off something like 7. So I should have negative 1 remaining. So there should be negative 1 copies of d sub n minus 2 plus n minus 2 times d sub n minus 3. Okay. I'm going to star this one as well. Taking my 3 starred pieces and putting them all together, this is a string of equality, so we have equality all the way through. So we should have n times d sub n minus 1 minus d sub n equals this next piece, which is, I'm going to write as negative n minus 1 d sub n minus 2 plus d sub n minus 1 equals n minus 2 d sub n minus 3 minus d sub n minus 2. This is my first starred piece. This here is my second starred piece. This here is the third starred piece. And I might have rearranged them a little bit by just rearranging the terms, but it's just commutativity of addition. Okay, so what does this mean? That's a good question. Okay. So in general, what does this mean? So you can trace back. If you have 2 terms, you can trace this back to something that's equal to something 2 smaller. So the implication is that if n is even, you have to have that 4 times d sub 3 minus d sub 4 equals 2 times d sub 1 minus d sub 2. What we know about derangements, there's no derangements of a 1-element set. There's 1 derangement of a 2-element set. So this is equal to negative 1. And this has to be equal to, as you decrease by 2 each time, this was the same thing as the same parity as, so I'll write if n even over here, n even. This says that, okay, how do I want this to go? Something bigger than the other one. Yeah. So this says that n times d n minus 1 minus d n equals this. And if n is odd, we have to have n times d n minus 1 minus d sub n ends up being equal to, as you trace through this equality, you can keep recursing, you get 3 times d sub 2 minus d sub 3 ends up being equal to d sub 2 minus 2 d1. After you get to this end, number of derangements of a 2-element set is 1, minus the number of derangements of a 1-element set is 0, so it's 1 minus 2 times 0, which is positive 1. Okay, so what does this mean? When n is even, I'm going to take this first piece. This thing over here is equal to negative 1. All right? So when n is even, d sub n, or negative d sub n equals negative n times d sub n minus 1 minus 1 multiply this by -1, and you get d sub n equals positive n times d sub n minus 1 plus 1. Okay? And if n is odd, you get negative d sub n equals negative n times d sub n minus 1 minus 1. Sorry, actually, this is a plus. Oops. Hold on. Plus 1. So you multiply by -1, you get positive, positive, negative. You get d sub n equals n d sub n minus 1 minus 1. And so again, if n is even, then -1 to the power of n is positive 1. If n is odd, -1 to the power of n is -1. So in each of these cases, we have this is equal to n times d sub n minus 1 plus -1 to the power of n for the case of n even. And in the case of n odd, we have this equal to n times d sub n minus 1 plus -1 to the power of n. So it's true for the case of even or odd for n power n being the 2. This is sort of gnarly, I would say.
Also, Ben, does this only work if n is at least, what, say 4? Because we have to assume that d sub n minus 1, or like we go down to this
Yeah, the recurrence really wants this to be bigger than 4 or something like that. You can show it's true, like just directly for smaller values. So I think if I were to do this in particular, and in the interest of more time, you need n to be a little bit bigger. But it is true, I promise. It's proof by intimidation. It's true, gosh darn it. Okay, cool. Big camera. We're getting into, I think, what I'm going to finish off with, which should be fun. Is not this one. I'm going to skip it. I'm going to do some Catalan numbers. Do some more fun recurrences. Cool. All right, so we're going to look at the Catalan recurrence right now, which shows up in a few different ways. Thank you, though. We're going to find a recurrence for the number of ways to triangulate a convex polygon. I'm actually going to change this. Instead of being n sides, I want to do it with n minus 2 sides, which sort of just doesn't matter. Because the idea is polygons with 1 or 2 sides isn't really a thing. So they only really start off with having 3. So I'm going to let C sub n be number of triangulations of a convex polygon with n plus 2 sides. So when n equals 1, we're looking at a triangle which has 3 sides. When n equals, which is the first term in the recurrence. When n equals 2, we're looking at a quadrilateral. So what is a convex polygon? I'll sort of just give a picture. This here is convex. Convex. Okay. This thing right here is not convex. Okay? And so the reason, the issue with this being not convex is this sort of a situation right here, this sort of the situation here. In general, convexity means if I have 2 points, I should be able to draw a line between them and stay within my shape. I can't do that right here. Okay, so this is not convex. But what's something interesting about a convex polygon, and we're going to use this to our advantage. If I draw a convex polygon, however I draw it, and I split it with a line, I draw a line through it. No matter how I draw a line through, I split it into 2 smaller convex polygons. This is sort of an important idea that we're going to use. Okay. So this is what's going on with convex polygons. And now we can look at what are triangulations. So a triangulation okay, so the smallest sort of polygon is a triangle. And if we have some general polygon, like this, if I want to triangulate this, I want to split this into sort of a gluing together of triangles. So maybe one way to do this is I can connect all the points to one, like down here. Now I have this here as a triangle, this is a triangle, this piece right here is a triangle. There's another way to have done this though. I mean, there are several ways to have done this, as we'll find. All right. I could also have done this triangulation here, like this, as another valid triangulation. But I'll show something that isn't valid. So when I'm making these triangles, I am drawing a line between 2 points. But what I'm not doing is this. I'm not drawing a line between these 2 points and a line between these 2. I can't have these lines I draw in the middle cross, ever. So this is not okay. Cool. Not illegal. Okay, so you can't do that. So this is what's going on with the triangulation. All right. So let's look at this. Let's figure out what is C sub 1 first, maybe. C sub 1. This is the number of triangulations of a convex polygon with 1 plus 2 sides. So this is the number of triangulations of a triangle. So I have a triangle, and I want to figure out the number of ways to split this into triangles. You just do nothing. There's one way to do it, and it's to do nothing. Cool? And then in general, I'm not going to count them, but C2 is the number of ways to split a convex, I'm going to call it a four-gon, four-sided polygon, into triangles. So we have some shape like this. You can either draw this line, or you can do this one here. So there end up being 2 for this. All right. Clearly you can't draw another line. To triangulate, we have to draw a line between vertices. And any 2 vertices here are either paired, or trying to pair them would cross another line. So it wouldn't be a valid triangulation. All right. We only need C1, I think, to count this or start this recurrence. But C2 equals 2. We'll make a note over here. Okay. Okay. What I want to do now is I want to look at C sub n. So it's the number of ways to triangulate a convex polygon with n plus 2 sides, right? And vertices. So what I want to do is I want to have some sort of polygon. I don't really know how many sides it has. Maybe it looks like this, except for convex. All right, it looks like this. What I want to do is I want to think about the vertices being in order. So if it has n minus 2 or n plus 2 sides, it'll have n plus 2 vertices. So I just want to go around, maybe in clockwise fashion, and label them V0, V1, V2, V3, V4. Maybe I'll do something over here. Maybe it goes off This is vk. It continues in this convex fashion. And finally, it ends up with this vertex here is vn plus 1, and vn plus 2 is the end. Okay. So I have all these vertices. Now, what goes on? When we make a triangulation, suppose I've triangulated this thing. I want to look specifically at the line segment formed from vn plus 2 to v0, this line segment right here. That's going to end up being in a triangle, in my final triangulation. So it's going to be these two vertices, and a third vertex in my triangle outside of those two will form a triangle. So in a completed triangulation, vn plus 2 and v0, because they share an edge, will form a triangle with some other vertex. We're going to call it maybe vk, v sub k. And so I've got that one over here. It's like I knew it was coming, except for I don't like this picture. Maybe we'll put v sub n minus 1 over there. So maybe this is my triangle. Okay. So I have this triangle right here. And I know that in a completed triangulation, everything that's above, between we have now a smaller convex polygon formed by vk plus 1, vk plus 2, all the way up to vn plus 2. Then it comes back along this line. So everything above this line is a convex polygon. And maybe more easy to see down here in this first part, v0, v1, v2, v3, v4, all the way up to vk also form a convex polygon. Okay. So what is this? So v0, v1, up to vk form a convex poly with, every time you laugh, I have to check the board now. They form a convex polygon with, okay, there's k plus 1 vertices, so there's k plus 1 sides. K plus 1 sides. This can be triangulated in how many ways? Convex polygon with k plus 1 sides can be triangulated in c sub k minus 1 ways. So this is where our idea of recurrence is coming into play, right? We have this thing with fewer sides, and we know sort of what's going on with anything with fewer sides or anything earlier on in recurrence. This number of ways to triangulate this piece is c sub k minus 1. Similarly, v sub k, v sub 1, or v sub k plus 1, v sub k plus 2, up to v sub n plus 2, form a convex polygon, poly with n plus 2, is it minus k sides? Yeah. Minus k vertices, so this is n minus, yeah. Oh man, it's the plus 1 situation. Okay, what's going on with this? Well, if this was, if k was 3 and n was 5, it would be 7. And so it would be 3, 4, 5, 6, 7, which would be 7 minus 3 is 4. Okay, with n plus 2 minus k sides. Okay, that can be triangulated. In one of number of sides minus 2, so that should be C sub n minus k ways. Okay? So let's think about this. We can again do a double count. I'm erasing this, but we'll go through with it. So I'm going to put number of triangulations of an n plus 2 gon of a convex n plus 2 gon here. On one side, I'm going to say that that should be equal to C sub n. And on the other side, I'm going to split it up based off cases, based off of the partner in a triangle with V0 and V sub n plus 2. So that can be anything. It could be V1, V2, V3, V4, V5, all the way up to V sub n plus 1 equals the sum from, so over the cases, it should be I equals 1, or maybe k equals 1, up to n plus 1 of the number of ways to fill out a triangulation with V sub k being the partner. So that should be C sub k minus 1 times C sub n minus k. So this is a number of ways. So we say pick a partner to be in a triangle with V sub n plus 2 and V sub 0. And then fill out the rest of it in a triangulation. So this is to do the top piece. This is to do this piece down here. This will be to fill out the triangulation up here. So what does this say? This says that C sub n is equal to this piece right here. And this is a sum of products of earlier terms in our recurrence. So every other recurrence we've had before has maybe had terms multiplied by numbers, or maybe they're on their own. Here we have a sum of a bunch of terms that are products of terms in our recurrence. So this is much more complicated, but it ends up having a nice closed form that maybe pops out later on. We won't dally with that. And I will say, if you want to, you can re-index this. Instead of going from k equals 1 to n plus 1, you can go from, this should be k equals 0 to n of c sub k. Instead of plugging in 1 and doing c sub 1 minus 1, you can plug in just 0 times c sub n minus k plus 1. So this is another way to write this, and maybe this is more natural for some.
Mark insists that your vertex numbering is off and that your polygon has n plus 3 sides. Instead of probably, you wanted n plus 2, am I right?
My polygon should have n plus 2 sides. The slide is off. So the slide is wrong. This should have n plus 2 sides.
Okay, if you start at B naught, then it has n plus 3.
Oh yeah, okay, so this should be, this should be n plus 1, shouldn't it? Okay, that's what's going on. I have n plus 2 vertices, yes. This is totally right, okay. So this is n, so this should be from up to n plus 1. And so my indexing should go from k equals 1 up to just n right here. And so this would go from k equals 0 to n minus 1. Mark is correct.
I literally just parroted what he said. I have
Yes,
no idea what
well
I
thank you,
said.
Mark. Yes, that's very kind of him. Yeah, you're right, because there's n right here, and then there's 2 more, so there's n plus 2 total. That works. Good eye, Mark. Okay, cool. So this is the number of triangulations, convex n plus 2 gon. It's given by this, and we have our earlier terms. Cool. This is a nice recurrence, but I know what you're thinking. You're thinking, what a contrived way to come up with a recurrence, and that'll never come up again. I have another problem. It's, I don't know, maybe suggestively named Catalan 2 right now. This is a good one, yeah. So Catalan 2, we're going to find a recurrence for the number of lattice paths using steps 1, 0 and 0, 1, returning to the point n, they have to start at the point 0, 0, and never rising above the line y equals x. So I don't know if anyone's been here for 7 hours or 6 hours, however long it's been. But I defined an integer lattice some time ago. So we're again looking at the integer lattice. We can just think about this as being, here we have points in the plane, and this is 1, 2, 3, 4, 1, 2, 3, 4. And so the points in the lattice are the points in the integer lattice. So they're points with integer coordinates. Okay, so we have these points, but also these points along the axes. 0, 4, for instance, is a pair of integers. And so a step 1, 0, if you start here at the origin, that means you move one space to the right. You can think of this as moving like east with some cardinal directions. So a step of the form 1, 0 is a step east. A step of the form 0, 1 is a step up. Okay, so as going 1, 0 is a step over, and a step of the form 0, 1 moves up. All right. And the idea is we have this line, which isn't perfect here. We have this line right here that I'm going to put in. This is the point line y equals x. So I want to think about a way to move through this lattice by just moving east and north, never traveling above this line. And I want to think about a way to do that. So I have some sort of path that goes here, but it ends up at some point along the line y equals x. Again, any point of the form n, n will be on the line y equals x. So I'll just draw a picture of some path to the point 3, 3 that does this. Maybe this is 1, move this way, move up, move over 2, move up 2. And so this is we call this a ballot path sometimes. So this is a lattice path using steps 1, 0 and 0, 1, never rising above y equals x. You're allowed to touch it in the middle, but you're never allowed to rise above it. Okay. So I want to figure out what this is. How are we going to define this? Maybe we'll have a 0 in this case. I don't know if this is my good pen. I'm just going to get a new pen. Carpal tunnel. For the last. This is going to be the last one, I think. Yeah. Or it didn't have to be, but it is going to be. Okay. So C0 is the number of ways to start at the origin, 0, 0, and move to the point 0, 0, taking steps over and right. You can't do, if you start at the origin, you only are going to move away from it as time goes on, or as you take more steps. So you can't do anything. You just have to do nothing. So there's one way to do this. Okay. Now, what about C1? It's the number of ways to start at the origin and move to the point 1, 1 using steps over and up, but you never rise above the point, above this line. So you'll notice you can't take a first step up because then you immediately rise above the line. Your first step has to be over 1. And if you want to get to this point, you can never go backwards, so you have to take your next step, be just straight up. So C1 also equals 1. All right, getting a little hoarse. I guess it's called a pony. Okay, so we have this. Now I want to think about, in general, C sub n. And I'm going to draw what I would call a schematic, or I often call a schematic, which is just sort of like a sketch to sort of get the point across to you. So I'm going to draw my axes. This is my x-axis and my y-axis. And I'm going to sketch in the line y equals x. And up here, I have my point n, n. So any ballot path I take traverses through this region, goes over and up and over and up and over and up and over and up. All right? However, it never rises above this line. And so the first thing for us to notice is the very first step I take has to be over to the right one. It has to be a 1, 0 step. First thing I do is I move over to the right one. Otherwise, the only thing I can do instead is move up, and that's not a ballot path because it runs above the line. So what I want to do is again establish a double count, but we're all masters of the double count now, so I'm not going to count C sub n. But I'm going to think about ballot paths based off of the first time they return to the line y equals x. So this ballot path that I have right here to the point 3, 3 returns twice. It returns at the point 1, 1, and it returns at the point 3, 3. So what I want to do is I want to think about I return at some point, this here is k, k, and I want k, k to be the first point along this line that I return to. Now that could be the point n, n. I have to get back to this line eventually, and it could be right at the very, very end. That's allowed. But I want to think about what's going on. Okay, so my first step I take is I go over here, and then I do some stuff, and I know I return to this line k, k. What's the last thing I can do before I get here? I have to have moved up. I couldn't have come from the left because I would have been above the line y equals x. So the last thing I had to do was move up to this point. I had to move up from the point, this is k, k minus 1. So what's going on? So the first thing I do is move to the right. The last thing I do before I get to k, k is move up. And I know I never hit this line right here in the middle, okay? So I never take an up step from there. So the idea is I want to look at this region right here. Here. In this box, whatever I do in here can be viewed sort of as a ballot path itself. It never moves above this line, y equals x minus 1. Because if it moves above it, it moves along to this point right here. And we know that k, k is our first return. I only use steps over and steps up. And I get to this point right here, which is like k minus 1 steps away. So I can do this piece right here, do this in c sub k minus 1 ways, or one of, in one of c sub k minus 1 ways. And then what happens after this? Now I get to this point k, k. And from here, I never rise above the line y equals x. I take steps over and up. So for the rest of this, I finish with a ballot path that can be thought of as being translated backwards to being a path starting at 0, 0 and ending at n minus k, n minus k, right? If you move the path that you take through here back to the origin. So I can do this in one of c sub k minus 1 ways. Okay. So let's put this all together. C sub n then, which is the number of ballot paths, should be equal to, we split off based off of the first point we return at. First return is k, k. So let's sum over all those cases. K equals 1 up to n. The first return can be 1, 1. The last return can be n, n. And then we do the number of ways to start our path. C sub k minus 1. We move up, and then we complete our path. Times c sub n minus k. So this here is our ballot recurrence again. This is the same thing we saw after a little bit of mark-assisted changing on the last problem. So this is the same recurrence. And so the idea, I think this is maybe startling. You all doubted it, but I'm here to say that this recurrence is here to stay. Okay. Yeah, all right, any questions on this? We're about out of time. For me, we are halfway through this marathon. Yeah, feels pretty good. Well, I will be signing off. We'll take a couple minutes before our next speaker, which will be Corey again.